everybody. Welcome back to Mathematical Statistics. We are talking about minimal sufficient statistics. We've been talking about sufficient statistics for a while, which are functions of the data that you can use in place of the data and not lose any information about the unknown parameters. And then we talked about complete statistics, which were usually also sufficient, although you can have a complete statistic that is not sufficient. Check out the handout I posted on Canvas yesterday. And completeness is a stranger concept that gives us that there is only one function of a complete statistic that is unbiased for whatever you're trying to target. By the way, and I don't really talk about it this way, but if you're reading stuff or listening to your own instructor, when people talk about complete statistics, they talk about there being no unbiased estimators of zero, or at least no non-trivial unbiased estimators of zero. So again, you don't need to know this for this class, but what does that mean? So if S is complete and you have a function of S whose expected value is zero, completeness says that G of S has to be zero. Now, this is a with probability one statement. It doesn't mean the function G is identically zero. It means G for the values that S could possibly take on is going to be zero. But from this first line, we've got that G of S is an unbiased estimator of zero. And if S is complete, that just gives us that G of S is zero. So I said that completeness guarantees that you have no non-trivial unbiased estimators of zero. Of course, zero is always unbiased for zero, but nothing more complicated than that is going to be unbiased for zero when you have a complete statistic, a function of a complete statistic. So I don't know. I don't, you're not going to need that in this class, but you might read that somewhere. Okay, so the third thing, sufficient statistics, complete statistics. We've been talking about minimal sufficient statistics, and these are sufficient statistics that have reduced the dimensionality of the data to a vector of statistics that is as low as you can go, kind of. A lot of people make the mistake of saying, if I have a sufficient statistic that is one-dimensional, I certainly can't go lower than that. It must be minimal sufficient. But that's not quite right. That's not the definition of minimal sufficiency. So the definition of a minimal sufficient statistic is something that is, number one, sufficient, and number two, a function of any other sufficient statistic. We had an example last time where we looked at a sample of size 1 from the normal 0 sigma squared distribution, and the statistic x1, which is the entire vector of the data, that's always sufficient. So I'm calling it S1 for a first sufficient statistic. S2, x1 squared is what you would get if you went for the exponential family factorization. So this first one is sufficient because having the entire data set, which is only one piece of data here, is always sufficient. And the second one is sufficient by the exponential family factorization, which means it also happens to be complete and sufficient. Now, S2 is a function of S1. In other words, x1 squared is a function of x1. If you know the value of x1, you know the value of x1 squared, but not the other way around. If you know the value of x1 squared, then x1 could be plus or minus the square root of that. So in this example, it's really only this one I claim is minimal sufficient. And here are examples of two sufficient statistics. One is a function of the other, but not the other way around. So S2 is minimal sufficient, but S1 is not minimal sufficient. We have a couple of ways of finding minimal sufficient statistics. The easiest way is Bahadur's theorem. Actually, I'm not going to recap this. I'll just write it. So Bahadur's theorem says if you have something that is complete and sufficient, it must be minimal sufficient. We can get a complete and sufficient statistic using exponential family factorizations a lot of the time. We can't when our parameters are in the indicator, but hopefully we can use the factorization criterion to get something that's sufficient. And if we're looking for something minimal sufficient, I would refactor that joint PDF over and over again to get the lowest dimension sufficient statistic, and hopefully you can show it is minimally sufficient. So again, if it's complete and sufficient, it's minimally sufficient, you're done. But if not, you can use this theorem we had last time that we saw an example of how to use it last time, but we haven't proven it yet. And that's what I want to start off with today. So I am going to suppose that I have some data. I have like a capital X1 through capital XN IID with some PDF F of X and theta is a parameter that could be one-dimensional or higher dimensional. Given that setup that I'm too lazy to write, a statistic t, which is going to be some function lowercase t of x, is minimal sufficient if. So I'm going to give you a sufficient condition for minimal sufficiency. This is not an if and only if, at least at this point of the statement of the theorem. So it's minimal sufficient if we look at the joint PDF of the x's and theta over the joint PDF of still the x's, but evaluated at some lowercase y1 through yn. So I only have capital X1 through capital XN here. These PDFs are the same function, but for one of them, I plugged in lowercase x1 through xn, and the other lowercase y1 through yn. But nowhere here are there new random variables, capital Y1 through capital YN. So this is theta free, if you will. You might say independent of theta, but the word independent in probability and statistics can be a little bit of a loaded word. If and only if the function t of little x is equal to t of little y. So we used this last time. This can help you show that something is minimal sufficient, or it can help you pop out a minimal sufficient statistic in the first place if you don't have any guesses. You can form this ratio. We did it last time for the Bernoulli distribution, and we saw that the ratio of these PDFs was free of the parameter p, if and only if the sum of little x's was equal to the sum of the little y's. And therefore, we had that the statistic t as the sum of the x's was minimal sufficient for the Bernoulli distribution. I want to prove it this time, but before I do, I want to say something about this ratio all the way on the left side. This is, I don't know if I've used this terminology before. I kind of think I have. This is known as a likelihood ratio. You'll see this phrase a lot in statistics, and you'll see it a lot in, what's coming up in the remaining couple of weeks of this semester. Recall that a likelihood is any function proportional to the joint PDF. So if my joint PDF started off with like a 1 over square root of 2 pi to the n or something like that, it would be both in the numerator and the denominator, and it would cancel in this ratio. So I don't need to include those multiplicative constants. In other words, and my notation sucks for this, but this ratio is like an L of theta over an L of theta. So this is why I said my notation sucks for this, because my likelihood notation completely hides the x's and the y's. So right now, this ratio I've drawn looks like it's 1, but one of them is the likelihood based off of the x's, and the other is a likelihood based off of the y's. So I'm not going to write that. But for this reason, the ratio here of joint PDFs is known as a likelihood ratio. Okay, so we want to prove that this is true. So let's start off with the assumption that we have a statistic. And there's no typo here in this theorem. I'm not starting with the assumption that we have a sufficient statistic and showing that it's minimal. I claim that this if and only if property here gives you sufficiency as well. So I didn't miss out on writing the word sufficient here. I don't need it. We are going to get that from this property. Let's call this property like star. So I'm going to start off by assuming that star holds for some statistic t. Let's show it's minimal sufficient. There are two things to show. Part 1 is to show it's sufficient, and then part 2 is to show it's a function of any other sufficient statistic. So let's do part 1. Let's show t is sufficient In the interest of time and the interest of interest, I think I'll just do this for discrete random variables because we're really not going to be talking about minimal sufficiency much more in this course. So we don't need, I was going to say as deep an understanding, but it's not harder to prove in the continuous case. It's just more intense notation because joint PDFs are no longer joint probabilities. So I am going to prove this in the discrete case where our x1 through xn are discrete random variables, just to make the notation easier. To show t is sufficient, we should consider the joint probability that x1 is some little x1 out through xn is some little xn, given that t equals little t. This is the first time I've used this notation, but I'm using little t to be a couple of things. And so this may be the function t with the little x's plugged in. I used to always give a different notation for this and kind of make it kind of curly so that this lowercase less curly t you could see was that function with lowercase letters plugged in. I hope this hasn't been too confusing, but this isn't the first time I've done this. Okay, what do we want to show? We want to show that this is theta free, and that is how you show that t is sufficient. If I write this out, we get two pieces. We get 0 if this lowercase t over here is not equal to the function t of these lowercase x's over here. And then in the case where t is equal to the function t of the lowercase x's, when you go and write this conditional probability out, you get the n+1 way intersection in the numerator and the marginal probability that t equals t in the denominator. And then because we're in the case where t equals t of x, the t equals t in the numerator is redundant and we get to drop it. So we've seen this a few times, so I'm not going to write out. I'm just going to say that and then write it down. But let me know in the chat if you're not okay with this move in the proof. Okay, so by the way, another point of notation falling apart on me at this late part of the semester is we want to show that this is theta free, but we don't know it's not theta free at this point. So I probably should have a theta in there. It's like we started the semester with PDFs that looked like this, f of x, and then we expanded them into things that look like f of x semicolon theta to show that dependence on theta. So I kind of want to put a semicolon theta in here, but I think it's really messy with conditional probabilities and conditional PDFs. And that's why I've left it out. But right now, as far as we know, this is a function of theta until we've proven that it's not. Same thing here. This is a function of theta. It's a joint PDF for the x's, and their distribution depends on theta. This is most likely a function of theta as well, because t is some statistic formed with the x's, and if you try to find the PDF or PMF for t, that's likely also going to depend on theta, but hopefully they cancel so that overall, this does not depend on theta. Okay, so I want to rewrite the denominator, that t equals t probability, in terms of the x's. And to do this, I first want to just do it by example. I'm going to just do a little aside, and then I'm going to erase it. So if you're taking notes, probably don't want this in the middle of your proof. Suppose that I have a couple of random variables just to give a really concrete case, like an x1 and an x2 living on the space -1, 0, and 1. And maybe my statistic t is x1 squared plus x2 squared. And maybe I want to write down the probability that t equals 1. If I know probabilities for the x's, the way I would approach this is to rewrite this in terms of the x's. This would be the probability that x1 is -1 and x2 is 0. Or we can get the disjoint event, so add the probability that x1 is +1 and x2 is 0. Or we could get the probability that x1 is 0 and x2 is -1, or the probability that x1 is 0 and x2 is +1. So if I want to write a probability for the statistic t, I could re-express it as a sum of a bunch of probabilities involving the x's. And that's what I'm going to do up here. It's just going to look weirder because it's not going to be this nice concrete example, but that's all I'm about to do. Okay, let me copy and paste here. And I want to rewrite this denominator. So I am going to rewrite this as the probability. Now I want to look at all the x's, and I want them to run over a different value. So I'll say, circle this, get some color coding here. X1 is like a Y1, out through Xn is a Yn. And then I want to sum over all points little y1 through little yn such that the function t of the little y's is equal to this little t. Right? This little t is like the 1 from that example. And yeah, so that's all I'm doing. Hopefully that makes sense. This is not 1 now, but it was in that example I had written over here a moment ago. Okay, so I am going to rewrite this, not rewrite this. I'm going to put 1 over this circled thing here, and then 1 over the circled thing down in the denominator of this giant fraction. And then I'm going to pull this inside the sum. So that leaves me with 1 over the sum over all y such that t of y equals t, and then this probability divided by this probability. But these are joint PDFs. So this is going to be the joint PDF for the x's with the little y's plugged in over the joint PDF for the x's with the little x's plugged in. There's only one joint PDF here, and there are no random variables y1 through yn. So I'm taking one single joint PDF, and sometimes I'm plugging in little x's, and sometimes I'm plugging in little y's. So that's what we get when we do all that pink circle manipulation there and rewrite those joint probabilities as the PDFs that they are, or PMFs. Okay, we are assuming that this property star is holding. So if we're in the case where t of little x is equal to t of y, then this ratio, and therefore the reciprocal of this ratio, is theta free. And we are in that case because the second line, the second line of this piecewise defined thing has that our t of the little x's is equal to some t. And then the second line of this version has that the t of the little y's is equal to that t. So this part here implies that t of the little y's is equal to t of the little x's. And so by property star, this likelihood ratio is theta free, since t of the little x's is equal to t of the little y's by property star. And there's no other thetas anywhere there. So this entire thing is theta free. And this entire thing was the joint PDF for the x's, given that statistic t. We got that this was theta free, and therefore we have shown that t is sufficient. Back to the bottom here, it wasn't there very long. So we're done with part 1 of this proof. We also want to show that it's minimally sufficient in the sense that if you have any other sufficient statistic, the t is going to be a function of that. Let's go. I'm going to put a number 2 here. It looks like I moved on to something, but this is the second step of my proof. So let's show that for any other sufficient statistic S, so this is going to be some other kind of function of the data. T is a function of S. How do you show something is a function of really anything? So the definition of a function is usually written out and not graphical, but you may recall the horizontal line test. If you have something that you graphed and looks like this is not a function. Because if you take a horizontal line, it hits it in more than one spot. And the idea is that if this is the x-axis, one value of x can produce different values of y. And the way this is usually written in courses and textbooks is if you want to prove that a function f, not related to the PDF, is actually a function, you want to show that if x equals y, this implies that f of x equals f of y. This is how you show something called f is a function. But I personally really hate this because that notation sort of is implying it's a function. How do you evaluate f at x if you don't have like a functional expression written out? So do whatever you want here, but I personally think it's a little easier to think of mappings first. And let me start with an example. This is another marginal note if you are writing this down. You don't want this in the middle of your proof, probably. So suppose I have some x values and some y values and a mapping between them. Maybe 3, 1, 4, 3, 0, I don't know. And for each x, I've got a y value. So maybe 4, -2, 7, 1, and 5. This mapping is not a function because you can see that I could plug in x equals 3 and yet get out different values. So this is not a function. Okay, so if we do have a function, then when you plug in the same value, you want to get the same value out. So even though I'm going to move to the left side of my screen, this is still part of my marginal note. Suppose that I have a function f of x. This is not a PDF. This is just a generic function on the side here. And I have like 3, 1, 4, 3, 0 as input, and 4, -2, 7, 4, 5 as output. So far, so good. This is appearing to be a function. Even though I have repeated inputs, I get the same output. So it's appearing like if these are all the values, if the x is listed here are the entire support for this function, f is in fact a function of x. And if I have another function of x, say g of x, that's going to take each one of these x values and spit out a number like maybe 1, 1/2, 5, -2, and 11. So this is another example of a function of x. Absolutely not. we want this value to be 1 because when I plug in 3, I need to get the same value each time. Okay, so now it's a function of x. I was wondering why you guys were looking at me like that. Okay. This g function also looks like, if this was all we knew about it, looks like it's a function of f of x because here I've got two of the same values for f of x, and g of those values must be the same. So using that idea where if you have duplicates here, you need to have the same value in the next column. If you have duplicates here, but they have the same value in this column, not only was g a function of x, but g is a function of f of x. I hope that makes sense. I hope I didn't make it worse. Maybe you guys were all good with what functions are before this, but I want to show that this statistic S is that is a given sufficient statistic. I want to show that T, which I claim is minimally sufficient, is going to be a function of S. So we're going to start off by supposing that S of some X is equal to S of some Y. But these take in vectors. So S of a vector X is equal to S of a vector Y. we're going to start with that assumption, and we want to show that t of x is equal to t of y. And then given what we just talked about with the mapping and the 3 columns, this will show that t is a function of s. The t function is a function of the s function, therefore the t statistic is a function of the s statistic. Okay, so in the interest of time, I'm spending way too much time on this given how important it is for this course. I am going to speed this up. Consider the joint PDF for the x's given that s equals some s. This is going to be the 0 or the probability for the x's over the marginal probability for s, depending on whether little s is equal to the function s of the little x's or not equal. I said that backwards. Not equal or equal. If I were to rewrite this, I am definitely going to take advantage of copying and pasting here. If I were to rewrite this with y's, then I would rewrite it with some y's. Y vector, y1, yn. I know I'm rushing and it's sloppy, but you know what I'm trying to write down. We've written this so many times. Okay. Because S is sufficient, we know that these are both theta free. So these circled things are theta free because S was assumed to be sufficient and we're conditioning on S. So by definition, the joint PDF for the x's, whether or not you're plugging in little x's or little y's, given S equals S is theta free. Therefore, if I look at the ratio of this to this, if I assume that S of x is equal to S of y, and that they're both equal to this S case, then the ratio of these 2 large pink circles is theta free. And the 2 large pink circles, if I took their ratio, I'm making a mess out of this. Let me write this. So the ratio, now we already have that it's theta free. So the probability that x1 equals x1 out through xn equals xn given s equals s over that same probability, but with little y's plugged in. We know this is theta free from the line above that's just off the screen. And yet this ratio, if you formed the ratio of these, you would get cancellation of that marginal probability for s. And this would end up being the joint PMF or PDF for the x's over the joint EMF for the x's with the y's plugged in. So we know this is theta free, therefore this is theta free. It's becoming really messy, but this thing on the right is the joint PDF for the x's, which itself may depend on theta, over the joint PDF for the x's, which itself may depend on theta. And because this is equal to this is a ratio of things like this, and because all of these things are theta free, this is theta free. Now we're assuming that condition star holds. And that condition star says that this likelihood ratio is theta free if and only if t of x is t of y. Now I started part 2 of this proof with the assumption that s of x is equal to s of y, and we got that t of x is equal to t of y, and that's what we wanted to show. But we're done. So we've got this theorem that says that you know that something is minimal sufficient if this kind of strange if and only if condition holds. And just as a reminder, here's the theorem and the condition. And we did an example last time. I do want to move on and not do another example. But we looked at the Bernoulli distribution. We made a ratio out of the joint PDF. We saw that the only way it could be theta free is if, it had something like not really literally this, but something like a p to the sum of the x's minus the sum of the y's. And the only way to get rid of the p was to have the sum of the x's equal to the sum of the y's. So we identified a minimal sufficient statistic that way. However, if you can show something is both complete and sufficient, then Bahadur's theorem has you covered and you don't need to use this at all. I had a few more things I wanted to say here, but they were more for fun than anything else. And I spent an awful long time on something that we're barely going to use. So I don't know, maybe I'll write that up for you if I have a chance, but it will be totally optional reading. Okay, so let's move away from minimal sufficiency, thank goodness, and talk about something known as an ancillary statistic. An ancillary statistic is a statistic. So let's set up our sort of base here. These guys have a joint PDF. They may be IID, maybe not, but they have some joint PDF, f of the vector x and theta, and then a definition. A statistic, t, which is some function, lowercase t of the x's, is an ancillary statistic if its distribution does not depend on theta, or more specifically, any unknown parameters. I'll give you an example in just a moment, but an ancillary statistic is, in some loose sense of the word, an opposite of a sufficient statistic. A sufficient statistic contains all of the information about theta, and an ancillary statistic really kind of contains no information about theta. Its distribution does not depend on theta. So, as an example, maybe we have x1 through xn, IID from a normal distribution with mean mu and variance sigma squared. And let's just assume that sigma squared is known, but mu is not. Then the statistic n minus 1 times the sample variance s squared over sigma squared. Now, I need sigma squared known for this to be a statistic, because a statistic is a function of the data, and it can't have unknown parameters in it. Sigma squared is just a number. So the thing I've written right here is just a function of the data and not of any unknown parameters. And we know in this case that this has a chi-squared distribution with n minus 1 degrees of freedom. And you can see that this distribution does not depend on the unknown parameter mu. So there's no mu here. And that means that this statistic is ancillary. I promise you'll care about ancillary statistics, but right now it's a definition. It's a statistic. It's something you can form from the data whose distribution is unknown parameter free. So they're going to be useful. And before I convince you of that, let me show you an easy way to find some ancillary statistics. Let's start with a definition. So suppose I have x1 through xn, IID with some PDF f of x and theta. The statistic theta is called a location parameter if f of x and theta can be written as f of x and theta is some function f naught of x minus theta, where the function f naught does not depend on theta. So take a function that doesn't depend on theta And if you replace all the x's with x minus theta, if that's like your PDF, then theta is a location parameter. For example, for the normal distribution, even if sigma squared is is both, even if they're both unknown, mu is a location parameter because, just for simplicity, let's say that it's known. Sigma squared. No, you know what? God, I don't need it. But f of x and mu can be written as f naught of x minus mu, where f naught of x is 1 over the square root of 2 pi sigma squared e to the minus 1 over 2 sigma squared x squared. And then if you plug in x minus mu for the x squared, that's how you get the normal PDF back. So there's an example of something that's a location parameter. Sometimes they're artificially introduced into problems. Like another example might be that we have x1 through xn IID with common PDF, f of x and theta and lambda, and maybe it's lambda e to the minus lambda x minus theta. This is looking exponential, except that minus lambda. And let's put an indicator for this continuous distribution saying that the x's take values from theta to infinity. This is just a shifted exponential distribution. Usually it looks like this, but now it looks like this, or even like this. This could be your theta, but it's shifted by theta units, and theta could be potentially negative. So here is another example. Theta here is a location parameter. Okay, so I have another definition for you. A statistic t, so some function little t of capital X, is a location invariant statistic. If you look at this function here, if t of x1 through xn, if you add like a constant, a real number c, the same real number to all of these, you don't change the statistic. So this has to hold for any real number c, for any c in the reals. An example is the sample variance. S squared equals the sum as I goes from 1 to n of xi minus x bar squared over n minus 1. If you consider like yi defined as xi plus c, then the average for the y's is the average for the x's plus c. And so if you form this statistic, you'll get like xi plus c minus x bar plus c. I'm just looking at the numerator, but the c's will cancel. Right, so this is going to be, and therefore this entire statistic is location invariant. What were we talking about? We're talking about ancillary statistics, and I have a theorem for you. Suppose we have x1 through xn IID with some PDF. If two things happen, if theta is a location parameter and t, which is some t of x, is a location invariant statistic, then I claim that the statistic t is ancillary. And that means, again, that its distribution is theta free. So let's prove it. I still haven't told you. So if you're not alone if you're wondering, like, did she say why ancillary statistics are important? No. We're just going through some motions right now. Let's prove this theorem. All right, I'm starting with the setup here, and I'm going to, for I equals 1, 2, out through n, I'm going to define yi equals xi plus theta. I'm not using just any constant, I'm using the theta parameter here. So let's find the joint PDF for the y's, y1 through yn. So this is an n-dimensional Jacobian problem, most likely. I suppose there's other things, other conditional arguments you can do to get this joint PDF. But I've got like a y1 equals x1 plus theta, and that's like a g1 of x1, but for our Jacobian problems in general, it could be a function of all of the x's, and a y2 is x2 plus theta, and that's g2 of x1 through xn, etc. And for the Jacobian problem, we want to invert this system. So we want to solve for the x's. x1 is y1 minus theta, x2 is y2 minus theta, all the way down to xn is yn minus theta. And if we form the Jacobian, this is going to be an n by n determinant. We're going to get dx1, the partial derivative of x1 with respect to y1, the partial of x1 with respect to y2, x1 with respect to yn, and then the next row is going to have all x2s, dx2, dy2. And so look at the upper right in the screen right now. The derivative of x1 with respect to y1 is 1. And with respect to y2, this derivative is 0. With respect to y3, it's 0, etc. X2, the derivative with respect to x1 is 0. With respect to y1, I'm sorry, x2, the derivative with respect to y1 is 0. With respect to y2 is 1, and we get zeros. And if you continue this, you'll see that we just are getting the identity matrix, and the determinant of that is 1. So the joint PDF for the x's, because these are IID, this is a product as I goes from 1 to n of f of xi and theta. And by assumption, theta was a location parameter. So this is a product as I goes from 1 to n of f naught of x minus theta. Okay, so we're ready for the joint PDF for the y's. I'm sort of switching notation back and forth from current to beginning of the semester. Let's look at the joint PDF for y1 through yn, y1 through yn, and theta. But I'm going back to our beginning of the semester notation with Jacobians. This should be the joint PDF for x1 through xn, evaluated at g1 inverse y1 through yn, out through gn inverse y1 through yn, times the absolute value of the Jacobian, which in our case was 1. So we're going to get this joint PDF, and in place of xi, I'm not going to get what I want. I can fix this though. I am going to go back up here, and I am going to define this. I'm so sorry. I'm going to define yi to be xi minus theta. The Jacobian will still be a determinant of a matrix like this. The Jacobian is still going to be 1, but all of these are going to be different. I'm going to have x1 is y1 plus theta, out through xn is yn plus theta. I'm so sorry about that. But when I plug in the yi plus theta, I'm just going to get f0 of y1 plus theta minus theta times f0 of y2 plus theta minus theta out through f0 of yn plus theta minus theta times the absolute value of 1. And so we get something that has no thetas in it. And by definition, f naught is not a function of theta. So no theta. So we've just seen that the joint distribution of y1 through yn does not depend on theta. Ooh, what are we trying to show? We're trying to show that our location invariant statistic is ancillary, is theta free. So let's look at, I'm make sure I set this up. Yeah, I have a t. Okay, so t is some function lowercase t of x1 through xn, and x1 is y1 plus theta out through yn plus theta. And if t is location invariant, which is our assumption, then this is t of y1 through yn, or t of the vector of the capital Y's. Now, this is a random quantity, but the distribution of the Y's is theta free, and therefore t of this new random variable or random vector we're making out of the Y's has a distribution that is theta free. So the distribution of t is theta free because we were able to write t as a function of the capital Y1 through capital Yn, and the distribution of those is theta free. Thus, t is ancillary. And that's what we're trying to show. So sorry, I had to go back and kind of fix that, but it's really not bad. Okay. One more definition and one more theorem before we get to the point of ancillary statistics. We've got this idea of location parameters and location invariant statistics. Now I have another definition for you. If I have x1 through xn IID from some distribution that depends on a parameter theta, theta is a scale parameter. This is the definition of a scale parameter. If f of x and theta can be written as f of x and theta is 1 over theta f naught of x over theta, where f naught of x does not depend on theta. This is the definition of a scale parameter. And within this definition, I'm going to just add a parenthetical remark. Theta is an inverse scale parameter if the f of x and theta can be written as a theta f naught of theta times x, where f naught is some function that doesn't depend on theta. So really, you can call them both scale parameters. You're scaling in both cases. But technically, when it's this way, it's a scale parameter. And when it's this way, it's called an inverse scale parameter. This is like the two different ways we write down the gamma distribution. I've been using the gamma distribution with beta as an inverse scale parameter, whereas some people have the beta being a scale parameter. Yeah, and so that would be an example for a gamma alpha beta distribution in this class when the PDF looks like 1 over gamma of alpha, beta to the alpha. x to the alpha minus 1, e to the minus beta x, and an indicator, but I'm rushing. Note that I can rewrite this as 1 over gamma of alpha, a single beta, and then beta x to the alpha minus 1, e to the minus beta x. And this is beta f naught of beta x, where f naught of x, let's just say alpha is known, but even if it's unknown, this we can take this to be x to the alpha minus 1, e to the minus x, and this is the function that if you plug in beta x, you'll get this back. So beta is an inverse scale parameter if you write down your gamma distribution as we have been writing it in this class. Okay, I have a theorem for you. I think this is completely guessable. I'm getting sloppier and sloppier. Oh, I don't have a theorem yet. I have to tell you about scale invariant statistics. So let me get that out there. Okay, so a statistic t equals some t of x is scale invariant if t, this lowercase t function of a constant cx1 out through the same cxn is equal to t of x1 through xn for any positive real number c. So that's the definition of a scale invariant statistic. And an example might be something like the max minus the min over a sample mean. I'm not going to write this one out, but if you have a bunch of data and you have a positive constant c, if you multiply every value by c, you're multiplying every value by c. And so the new, like if we let yi be cxi, the maximum for the y's is c times the maximum for the x's. You could get into trouble with this if you allowed c to be negative, which we don't allow. And like y bar is c times x bar, etc. And so if you write those all out, you'll get c's canceling here. And so it doesn't matter if you multiply the data by c or not, it's not changing the statistic. So this circled thing is an example of a scale invariant statistic. Finally, I have a theorem. I know you know what this is. It's just the other theorem. So suppose I have x1 through xn iid from some distribution with PDF f of x and theta. If theta is I'm going to leave a space, a scale parameter or an inverse scale parameter, and t is a scale invariant statistic. We don't really have a concept of an inverse scale invariant statistic because this, for all c, you could take 1 over c to be your c. Then t is ancillary. So the proof is very similar. I'm going to leave it to you. Let me know if you're having any trouble with it. And make sure you define your whys the right way. So you don't have to go back and fix them like I did. But very, very similar. And I think it's also in the notes if you want to check it out there. Why do we care about ancillary statistics? We have this concept of sufficient statistics, which kind of contain all the information about the unknown parameter, and ancillary statistics, which kind of have no information about the unknown parameter. And I got a couple of really cool theorems for you that can help you establish independence of certain random quantities. So I think I'll only get to one of them today. But please come back. At the beginning of next class, we're going to be doing Bahadur's theorem, which is an amazing theorem that you're not going to use very often, but one day you will use it and you'll realize that that was the best day of your life. I hope to hear from you in your future when you've used Bahadur's theorem. and it created the best day of your life. Okay, so suppose I have x1 through xn IID from some distribution with some PDF. Suppose that S is sufficient, and suppose that T is any statistic independent of S. Then we're going to show right now that T is ancillary. And this theorem, not very exciting at all. It's saying something that's sufficient and something that's independent of it, that independent thing has to be ancillary. It's interesting. But what I think would be much more exciting is if we could say, if something is sufficient and another statistic is ancillary, that they're independent. Now, that's not true. We need to add the concept of completeness. And if you come back next time, we're going to start with Bahadur's theorem, where we say if S is complete and sufficient and T is ancillary, then S and T are independent. And it's so important for us to be able to establish independence in probability and statistics. And I'm yammering on when I should be proving this theorem, but Bahadur's theorem is one that you will not use very often because the stars just need to align perfectly for you to use it. But one day you're going to have a really horrible statistic, really convoluted, made up of a lot of weird ratios of things, and another statistic. And you're going to be able to show they're independent using Bahadur's theorem. Whereas your friend doing statistics would maybe try to find a joint PDF of those two really horrible statistics, and they're not going to be able to do it, and they're not going to be able to establish independence. But you're going to quote Bahadur's theorem one day. One day. All right, I think I have a couple minutes, enough to prove this theorem. The less interesting sort of direction. So I don't know if I need to write this again. I'm going to suppose that S is sufficient. Then the joint PDF for the x's given S, I'm using continuous notation now. You could write this all discretely if you want, but this is theta free. That's the definition of sufficiency. So if you look at the statistic T, it's going to be some function, little t, of capital X1 through capital Xn. And if you look at the PDF for T given S, this is also theta free. The common sense argument is if the distribution of the x's given S is known, doesn't depend on theta, then when you take the x's and start making statistics out of them, it may be vector valued. So maybe T is the sum of the x's and the sum of the x's squared. In the universe where S equals S, if the distribution of the x's is theta free, then when you look at statistics, you're not going to be able to somehow get theta involved. I claim this is also theta free, but to prove this, you would do something like we had in the proof of the first theorem today. Remember when we wrote in the discrete case, the probability that T equals T was a sum over all Y of, probabilities involving the x's. So the probability that T equals T in the conditional universe where S equals S is going to be a sum over certain Y vectors of probabilities for X's given S equals S. And if S is sufficient, then this is theta free. And therefore this is theta free. So we get this result. But the easier way to think about that is the T's are just made out of the X's. And once S is given, if the X's don't have any information about theta, the T is also not going to have any information about theta. Okay, so running out of time. We had in our assumption here that T is independent of S. And so what this implies is that the PDF for T given S doesn't depend on S. I claim that this is just the marginal PDF for T. And this is, in fact, the way I define independence of random variables. I don't define it using joint PDFs and factoring, but if you want to see how to get from here to here, if this is not the way you define independence, this is the joint PDF over a marginal PDF. And then by independence, this is a product of marginal PDFs over a marginal PDF. And so you end up with just this. But again, this is my definition of independence. If you are given some information, it means absolutely nothing, as if you weren't given it. Okay, so I made a mess out of this. I made a lot of messes today. But this is equal to this, and this is theta free. Thus, this PDF for t is theta free. So t is ancillary. And that's what we wanted to show. So we were done with this proof. Okay, what do we just prove? If you have a sufficient statistic and another statistic that's independent of your sufficient statistic, that other statistic is ancillary. I don't really care that much about finding ancillary statistics. I care much more about finding or showing that things are independent. So we kind of want the counter of this theorem, which is not going to hold exactly. But if we add in completeness, it will. So next time at the beginning of class, we'll prove Bahadur's theorem, which says if you have a statistic S that is sufficient and complete, and a statistic T that is ancillary, S and T are independent. And these could be really complicated functions of the X's. And so it's going to be a really slick way to show independence of complicated functions of the X's next time on mathematical statistics.